Now we look at the next variation, and that is called coupled shear walls. So when you have two shear walls side by side, you can correct them, and depending on the stiffness of the connecting member, you can improve the performance of the shear walls. If you have say a total moment of capital M acting on two walls which are connected by pin-ended member, then the moment carried by each wall will be proportionate to the second moment of area. But once you combine these walls, then there will be certain interaction, and you will find that because there's a beam between the shear walls, to deform that connecting element, there will be a certain force needed, and that force will be transferred onto these walls, and that also can help to resist part of the moment. So because of that, when you connect two shear walls with a beam element, you can reduce the bending moment acting on individual elements. And we are going to discuss this in greater detail. So because of that, we'll just consider that coupled shear walls can give a better load distribution and a more efficient behavior by reducing the bending moment on individual walls. The advantage of having a lesser moment is then it will be easier to suppress the stresses on the wall due to the axial load acting on the wall. So there will be axial load, then bending moment, and another axial load. But you will find it finally gives a more efficient behavior and also reduced stresses in the walls, so that the wall can become more efficient and economical. So we are going to discuss this in greater detail, so we'll skip that without too much details. And then this is very important, and that is called wall frame interaction, wall frame structures. When we have more than 15 floors, then we can have certain amount of interaction between the frames and the walls. And we already know the wall is a cantilever, which is fixed at the base, almost fixed at the base. So it's a cantilever fixed at the base, and the deformed shape of the wall is a cantilever mode with zero rotation at the base, maximum rotation at the top. But when you look at the structure, these are the shear walls, these are the frames. They are all connected by the rigid diaphragm at each floor level. So what happens is, there will be a certain amount of interaction between the wall and the frame. So first we have to see what is the behavior of the frame. Frames deform in the shear mode or shear shape. Walls deform in the flexural shape. So like in the brace frames, we have wall, which is a very strong element, deforming in the cantilever mode or flexural shape. The frame deforming in the shear shape, but they are all connected by linked by the rigid diaphragm or the flow. So because of that reason, you'll find that the overall deformation of the structure will be like this. The wall deforms in the cantilever mode initially, but its deformation is controlled by the frame, which is stronger. So the frame controls the deformation at the top part of the building, and this controls the deformation at the lower part of the building. And because of this interaction, we'll get a very efficient structural form. And this structural form is used very much in the design of tall buildings. And this can actually provide us to provide sufficient lateral resistance to go up to 40 to 60 story range. 40 to 60 story range. So this is called wall frame interaction or wall frame structures. So there, the frame and the wall both are acting together. And let's see what are the advantages of wall frame interaction. One of the questions that I can ask is, now when you have a wall, concrete wall, and the frame is linked to it, we say the structure is braced. That means the lateral loads are carried by the wall and the deformations are controlled by the wall. Therefore, there's no chance for the frame to deform and collapse in an uncontrollable manner. And because the deformation of the frame is controlled by the wall, the frame can be designed as a braced frame. Frame can be designed as a braced frame. And braced frames, the columns need much less reinforcement than an unbraced frame. So there's an advantage. But here you can see in the top part of the building, the frame is stronger than the wall, and the wall deformation is now controlled by the frame. Then we have to ask the question, in the top part of the building, can we design the frame as braced, or do we have to consider it as unbraced? So what is the answer? In the bottom part, there's no problem because the wall is stronger and wall is controlling everything. The deformations are controlled by the wall. But in the top part of the building, frame is stronger, so the wall is weaker. Then you'll ask why the wall becomes weaker. Let's say, we are considering something like a 40-story building. And let's say we just, for the ease of calculations, we consider each floor is 4 meters of height. So the total height of the building is 160 meters. And let's say we are having a fairly long shear wall, 6 meters long. So 6 meters long and 160 divided by 6 is 26.6. So you can see when we consider a 40-story building, even though the wall is 6 meters long, it becomes fairly slender when you compare that with the overall height of the building. So what actually happens is, although the wall is almost fixed at the base with zero rotation, as you go to the top part of the building, the deformation of the wall can be significant, and because of the shape of the shape that you get in the deformation of the frame actually deforms less than the wall. So it looks like, frame is stronger than the wall, although wall itself is a strong element. The problem is it's too tall, so that's why it has become weak. Otherwise, it's not weak. So the question is, do we have to consider the frame as unbraced or braced in the top part of the building? Kannangara, you have to just give an answer, whether you think it's braced or unbraced.
So I guess unbraced.
Unbraced, yeah.
Yes.
So actually the situation is, when you consider wall frame interaction, it can actually reduce the deflection. but still the wall is a fairly strong element. Although its deflection is high, it cannot deform in a uncontrollable manner. So because of that reason, throughout the height of the building, we can consider the frame is braced. Frame is braced. So you can see we get an advantage by reducing deflection, and in doing so, we'll have lesser moments, forces acting on the wall. But at the same time, the main advantage of wall frame interaction will be lateral deformation could be significantly lower than wall acting alone. The bending moments in walls and wall assemblies will be less, and columns over the full height of the building could be designed as fully braced. So you can see clearly the advantages. So it reduces, when you consider the wall frame interaction, it reduces the loads on the wall, but at the same time it can ensure that the frame can be designed as braced. Now you can also see there's significant interaction between the wall and the frame. So because of that reason, in a tall building, when you consider wall frame interaction, you'll find that the topmost floor is also subjected to a significant level of lateral loading. And that lateral loading is coming due to restraint in the deformation of the shear wall. So if you consider the topmost floor of a 2-story building and a 40-story building, what do you think? This is a top floor. In a 2-story building, what is the column size that you use in the top floor? Maybe 250 by 250. But in the 40-story building, if you make the assumption that that is a top floor is slightly loaded, then you might say, okay, in the 40-story top floor also we can use a 250 by 250 column. But it is not so. What is the reason? The top floor frame in a 40-story building is subjected to a significant load transferred by the wall onto the frame. So because of that reason, you will need a column of at least 600 by 600 at the top of the building. So you cannot have very small columns at the top floor of a 40-story building due to this wall frame interaction. Can you understand that? Kaushalya?
Yes, sir.
Yes, Kaushalya, yeah, okay.
Excuse me, sir.
Yeah.
Are you telling we don't need to consider the whole? We are going to consider the whole frames as brace structures, or do we need to?
Yes. When you are designing, you will consider that the whole, all the frames are braced, right? The reason is even at the top, although we say the wall is weaker, I mean, wall is still capable of resisting the deflection of the frame. Now, why we consider braced and unbraced is, in the unbraced frame, if the frame becomes deformed, there's nobody to bring it back. Right? Whereas in the case of braced frame, if the frame tries to deform, the wall will say no. The wall will restrain the deformation. Whereas unbraced means, there's nobody to restrain the deformation. But in the case of wall frame interaction, if the frame decides to deform, then the wall will say, no, you cannot deform, because it's all connected by the rigid diaphragm. So that's why we say, although the wall appears weaker, it will not allow uncontrollable deformation on the frame, right? So because of that reason, we can say over the full height, the frame can be designed as braced. Is that clear?
Sir, but in the top floors,
Yeah.
the wall will also show a deflection.
Yeah. There will
Will
be
it
a deflection, but that deflection will be reduced by the due to the interaction with the frame.
Yeah, if the deflection of that wall higher than that of frame structure, then there will be an issue. No? So
No issue. The reason is now you should try to understand what I'm trying to explain. Now, in a brace structure, there will be a strong element that can control the deformation of the wall. Now, what is the problem with the unbraced frame? The problem with the unbraced frame is if the frame starts moving laterally, there's nobody to bring it back, right? No strong elements to bring it back. So that's why, in an unbraced frame, we design the columns to have columns to be very strong so that it will never move without any control.
yes.
Is that clear?
Yes, sir.
So that's the difference between braced and unbraced. In a braced structure, the columns cannot move in an uncontrollable manner because there are other elements that will prevent that kind of movement.
Yes, sir. Yeah.
Whereas in an unbraced structure, there's nobody. But in the case of wall frame interaction, the wall appears weaker because it's so tall. But if there's a weakness in the frame, then the wall will become stronger than the frame. So because of that, frame cannot have extremely large deformations, right?
Okay.
So that's why, we can say the frame can be, all the elements in the frame can be designed as braced. Is that clear?
Yes, sir. Understood.
Right? Okay.
Yes.
Any other
Thank
question
you.
like that? Any other questions? Okay. So with all these advantages, wall frame interaction could be very useful solution for the tall buildings. So it is possible to realize these advantages by using three-dimensional modeling of the tall buildings. So when you do 3D modeling, or automatically all those behaviors will be taken into account. Then we'll look at the other types of structures as well. And you can have structures like frame tube structures. And this frame tube is a concept introduced by one of the engineers called Khan. He's from Bangladesh, but he practiced in USA. He is the person who developed this particular structure. And his idea is that, the building is large. Then why do we want to, resist all the lateral loads by using a core in the center? And he proposed, let's use the facade to resist lateral loads. So in the frame tube structure, what we do is we create a perforated tube. So the ideal is to have a tube, no openings. But we can't have a building without openings. So what we do is by using so many columns and beams, we create a lot of openings. But all these openings are surrounded by beams and columns. And we create what we call a perforated tube. A tube with lot of openings. Tube with lot of openings. And when you do that, you get small windows. But when the openings are small, you can't enter the building. So at the ground level, you need large openings. So you provide large openings, but you need a transfer beam as well. So to make sure that people can enter the building, and all these loads that come here will be transferred onto the columns here, which are at a higher distance than the columns above. So you can see in the upper part of the building you get a lot of openings, whereas at the ground level you get large openings. And So the frame would need columns at 2 to 4 meter interval, and also it would need deeper beams along the perimeter. So here you get some deep beams, and it will become a fairly stiff tube, and you get opening. So it's a strong and efficient structural arrangement. And when you use this arrangement, you can easily go for about 50-story building. But only thing is the architect should like it. The architect does not like this type of building, then you can't use this particular structural form. So, but structurally it's fairly efficient. But there are problems as well. The problem is when the wind loads are acting, the wind load will act on this frame, and then the loads will be transferred onto this frame. So the load on this frame will be transferred onto this, and then this will actually resist the wind loads. And when this side resists the wind load, this will become the web, this will become the flange. So this will be the flange, this will be the web. And when the loads are acting, it's very useful if we can utilize the flange, because flange has a very big distance. But what actually happens is we get some effect called shear lag. Do you know what is meant by shear lag? Anybody who knows about shear lag? Now, one of the basic assumptions in the beam theory is plane sections remain plane. Plane sections remain plane. And shear lag means due to various deformations, due to shear transfer, some of these plane sections do not remain plane. Plane sections do not remain plane. Then we cannot, what you find is, although we expect the stress in the flange to be equal everywhere, the flange deforms more at the web, it deforms less away. So you will find the stresses are different. Stresses are different. That means, you know, the full flange cannot participate in resisting the moments. So this is called shear lag. And that's why, you know, even in reinforced concrete design, when you are designing a flange beam, we calculate the effective width of the flange. Can you remember? Now, you know, let's say we have a slab which acts with the beam, and the spacing between beams is 4 meters, then we don't say the width of the flange is 4 meters. We don't say that. We say the width of the flange is, say, something like 1.2 or 1.4 meters. What is the reason? The reason is shear lag. That means, you know, when you have a beam acting with the slab, we can say that the full flange width is effective from one center to the other. But in actual practice, what you find is that width is not effective. It is less. And the reason is plane sections do not remain plane in the flanges when the distance between the end of the flange and the web is high. So plane sections do not remain plane. And this is called shear lag effect. And this shear lag effect comes in here as well, because it's a fairly large building, something like 40 meter by 50 meter. So when the structure deforms laterally, we cannot expect it to keep the shape perfectly. So there will be variations in the shape. And because of that, although we have a very wide flange, which can actually effectively contribute, it will not contribute fully. So that is one of the drawbacks. And so you can see the gravity loads on the structure will be shared by outer tube. And you can also have additional columns and walls in the interior. When the lateral load acts, the perimeter frame aligned in the direction of the loading acts like a web. So this is the frame aligned in the direction of the load, that is the web. and those normal to the direction of the loading, this normal one, that will act as a flange. And at the entrance level, you need bigger openings and transfer beams. And the tube could be used with steel and concrete construction and could be used for 40 to 60 story range. And if you look at, if you can recall the World Trade Center building that collapsed due to the plane attack, it had this particular structural form. And that building went up to 110 floors, and it had this particular structural form. But it's a very large building. The reason is the area of one floor was equal to 1 acre. That means, it's a huge building. One floor is equal to 1 acre. So it's a very big building. And that building used this particular structural form. That is, having some columns in the center and then having large 45 meters trusses spanning between the center and the outer periphery. And so these are one kind of structure that that deviates a lot from what we generally use, what we call frames and shear walls. Is that clear? Right. Then you move on to the next type. Then this is a variation of the tubular structure. This is all tube in tube or hull core structure. So you have the outer tube and inner also you will have a core. So because this shear lag effect, this side becomes less effective, but because we have a core, the effectiveness can be improved. So this type of structures are a little more efficient than the tubular structures, and the outer frame tube and the inner core would interact horizontally and share the lateral load, thus improving the lateral stiffness. But the dominating member will be the tube because it's a massive structure resisting the lateral loads. But this can actually improve the behavior of the structure. And that is called hull core structures or tube in tube. And then another variation of that is to use a number of smaller tubes. Because the problem is when the tube is very big, it suffers a lot due to shear lag, or plane sections do not remain plane, effect is very high. So rather than suffering like that, what you do is you will use smaller tubes. So here you can see 9 smaller tubes have been used. And this is the arrangement that was used in this Sears Tower, having 104 stories, but was considered as one of the tallest buildings in the world for a very long period of time, until the Petronas Towers became taller, and now there are other buildings. But the Sears Tower was one of the tallest buildings for a very long time, and that particular structure used this bundle tubes. That means a number of tubes have been used. And what they have done is, with the height of the building, they have terminated some of the tubes. And by terminating some of the tubes, they created a nice shape for Sears Tower. So that's another variation. And then you can also have the braced tube structures. It's a tube structure, but in addition to the tube, you get a bracing as well. So some of these openings have been filled with concrete. So you get a nice pattern, but you lose some of the openings, and those filled openings will form a bracing on the outer surface. So the structure becomes fairly efficient in carrying lateral loads. And these doing the same thing for a steel structure by having very large bracings on the outer periphery. Then these one of the key applications in buildings, and especially when you have problems in controlling the deflections and so on. These outrigger brace structures are very useful. And what do you mean by an outrigger? Can anybody answer? What is meant by an outrigger? Outrigger is a kind of a truss or a big beam, deep beam, that connects the core with the outer periphery. It connects the core with the outer periphery. So here you have the core of the structure, here you have the outer periphery, and they are connected by these outriggers. So what happens is when the lateral loads act, without this outrigger, only the core will resist the lateral loads. But the moment you connect the core and the outer columns, the outer columns will also participate in resisting the lateral loads. Then the structure will become very efficient. And what we do is, now in a very tall building, when you want to control the deflections, you'll seriously consider these outriggers. And outriggers, the problem with outriggers is when you have a, say, concrete wall from the core to the outer periphery, you cannot move through that. So those are problems. So those are overcome by having what you call machine flows. A machine flow is a flow where you get water tanks and pumps and so on. So if you introduce one or two machine flows to accommodate all the other service requirements, then those machine flows can be converted to partition flows where you will be able to utilize these outriggers. And in many tall buildings, outriggers have been used, and especially when you exceed something like 50 stories, you will find that outriggers are very useful in controlling deformations. And the way that the outrigger works is it will combine the core and the outer periphery. And when the core and the outer periphery are combined, then you will get a bigger depth for resisting the lateral loads. With a large depth, you get a very high lever arm, and the outer columns are also now participating in the resisting the lateral loads. But one of the problems with these outriggers is we cannot be having outriggers everywhere. We will be having outriggers only in one or two planes. But there are columns on so many other planes on the outer periphery. So, but all those columns will not be acting together with the outrigger. So what we do is, from the outrigger, we will introduce something called a belt truss. Again, a deep beam that will connect all the columns on the outer periphery to the outriggers. So the columns on the outer periphery will be connected by the belt truss, and the belt truss will connect all those to the outrigger. So when the outrigger moves and deforms, the column directly connected to it, simultaneously you will be mobilizing all the other columns in the structure. So this way you can actually improve the performance of the building to a great extent. And then you'll ask how many outriggers levels. Generally, the optimum is about 2 outriggers. When you have too many outriggers, the effectiveness diminishes. So generally in a building, you might consider having about 2 outriggers, and in a very tall building, you might have a maximum of about 3 to 4 outriggers. Generally, the maximum number of outriggers is considered as 5. But we have to also keep in mind, outrigger construction is not very easy, because you have to do a lot of planning to make sure that that particular flow that you are having the outrigger can be utilized for some other purposes. Otherwise, it would be just a flow lost. The reason is the height of an outrigger beam can be about flow to flow height, something like 3 to 4 meters. So it's a very deep beam, and but it can be very effective in controlling the deformation of the structure. Then you can also have other variations like suspended structures and so on. And those are special variations where there'll be a large truss at the top of the building supported by the core, and then all these floors are suspended from this truss. So these are all special structures, and you can also have structures where you can see here the outrigger is used, core is used, the tube is used. All kinds of different systems are used in one building. Then you can also call it a hybrid building, and then there are some very special structures which should have actually been developed by the architects and engineers working together. So in those structures, rather than having separate frames and walls, you will go for some kind of three-dimensional arrangement with so many different combinations of structures. So this is called Hong Kong Bank building. If you just type Hong Kong Bank building on internet, you can see the actual structure of this one. And similarly, in places like Dubai, very special structures have come up. They are all a combination of all these different systems that we have looked at. So with that, I will stop today, and in 2 weeks time again we'll meet and we'll discuss more about these, and also the coupled shear walls, and also we'll talk about the wind loads acting on buildings and how to evaluate the accelerations and various other related parameters for the design of buildings.